What I want to talk about is something that me and my team are extremely passionate about, which is health extension in general. And specifically, we think that there's a revolution that we can help unleash when it comes to the preservation and organ transplantation world. Maria, Bill, Lee, and Mary, each of these are 4 real people whose lives were saved because of the breakthroughs that just over the last 25, 30 years happened in organ transplants. At the same time, they were only a couple of the lucky ones. Because if you look, this is just US data. Look at that yellow line, that's the wait list. So more than 120,000 people are waiting, not knowing if they're going to get an organ in time. And the gray line there, the 28,000, was the small amount of operations, organ transplants that we were able to do in the US last year. And that's the official wait list. If you look at what a lot of people are saying, it could be 10 times larger. And in fact, from a longevity perspective, about a third of all deaths have to do with organ failure. So a lot of people are arguing that you could radically also extend life if we had access to much better organ transplantation. Think about the emerging countries, developed countries, poor countries. If you take Semo here in Kenya, what would be a routine transplantation in Sweden, where I come from, or here in the US, won't even be attempted. So what's the solution? This is just that it's a much, much bigger problem around the world. So what's the solution? Well, to a large extent, it's going to be many different things. But one thing that could be enormous here is if you, in a long-term way, could preserve organs. So basically, store them in the same way that we do with cord blood, with stem cells, with sperm. That type of thing we've been doing for decades. If you could do that with larger organs, you could radically revolutionize the organ transplantation world. Save millions of lives. And there are other things you could do also. So tissue engineering is going to be a really good complement to this, so it's going to be really important for that world. But also if you take Sonia here, a girl who has cancer, going to probably be able to treat the cancer, but she's going to get sterile. If we could just take out the ovary, do the treatment with the chemotherapy, put the ovary back, you could both keep her fertility through life and also her hormone balance. Same with limbs. We're doing a lot of arm transplants and limb transplants. It could be fantastic if you had an inventory. So there are many, many, many things how this could really revolutionize the transplantation of organs. Just to name 2. So on the far right there, you see all of the hearts. So one thing that happens is if you look at the number of donors in the US, of the ones that are suitable donors, the ones that are deceased, we're only using about 25% or so of the hearts. So there's some estimates that say that the wait list for hearts, you could actually, if you could bank organs, you could get rid of the waiting list in 3 or 4 years. The cost, enormously costly. If you just take one piece of data, look at the cost of dialysis in the US, we're talking about $43 billion last year, just on the dialysis itself, not on all of the other problems around it. So it's a huge market opportunity there also. And yet, very few people are doing it. It's a little bit like artificial intelligence. Like in the 70s, there was enormous focus trying to crack this. They made progress, but then it kind of halted. And then now, there are very, very few teams around the world that are focusing on it. At the same time, it probably is achievable. What we've learned, what the experts in the field are saying, is that this is more of an engineering problem than that you need to come up with new things. It's more about combining the things. So I won't go through all of this stuff, but two concrete examples. So one is, to store something, you need to cool it. That's probably the main hypothesis. But if you cool it, you get what you have on the left-hand side, which is ice and crystallization, and it destroys cells. About 10, 15 years ago, there was a lot of breakthroughs that have to do with what's called vitrification, which means to glassify, where you're basically able to, in the same way that you put antifreeze in the car, use ice blockers and a chemical cocktail of cryoprotectants, and you can supercool also large tissue systems so that they basically, the atoms and the molecules stop moving. They're in a state where you can have them there indefinitely. Time has basically stopped, whether it's 10 years, 1,000 years, it doesn't matter. And it's doable. So in 2009, it was in a small rabbit model, but they succeeded, published in peer-reviewed journal, to do this with a rabbit kidney. So you're actually seeing a rabbit kidney down the right. Take it down to this cryogenic temperature where it could be forever, and then transplant it back into rabbit, sustain the rabbit's life. So there's a big proof of principle here that we can do it. It's just that we need to push it forward. We're at SU, so here's just a little bit of data on like how much more we're continuously learning. That if you look at the vitrification there on the right-hand side, it really is an exponential curve. And maybe this one is where we get most hope that this really is achievable, is that you have the integration of so many different technologies that didn't exist 10 years ago or weren't used when they tried to do this 20 years ago, that if you have that convergence, that integration of whether it's the proteomics and the genomics to understand the cell stress, whether it's one of the best papers last year that was published in Nature in this field was using computer simulations to understand the ice crystallization process, something that the author said she couldn't even have done 3 years ago because she didn't have the computer power. So there's a lot of convergence there. So if we basically know that it's probably doable and the need is enormous for the world, how are we going to get there? There's a couple of things, and it's marrying that big need with the market forces. And the thing that we think is needed is just a catalyst. So what we're doing this summer is we're bringing together the world's leaders for a grand symposium, basically a grand challenge symposium, to try to get both the cryobiologists and all of these other experts together to see if can we do a mini Manhattan project? How would that work? Another thing that you probably heard a lot about is the power of incentive prices. Whether it's the Ansari X Prize, go out to space, and then we launch the space industry, or Charles Lindbergh flying across the Atlantic. So that's a big thing we're going to do. Basically, first team to successfully cool down, or it could be another technology also, but successfully prove long-term storage of one of our big organs, or a heart, a liver, a kidney. Do that for an extended period of time, transplant it back into human or human-sized mammal with good function and survivability. And then the last thing is our call to action. A big part of the team is here today. We're going to be around. And it's basically what we've been learning when we've been talking about this, and we'll be showing the research that's behind the breakthroughs that are happening, the incremental ones, is that there's a lot of interest. So we already have angel investors who are want to be part of this network and see the teams, potentially invest in them. We're having conversations with some VCs, following up with a second conversation with Google Ventures on Friday, for instance. So if you're in that world, we'd love to talk to you. Same if you're at one of, say, a biotech company or a pharma company, knowing the high throughput screening to understand the toxicity or the cryoprotectants. Creating that ecosystem around these research teams that we're catalyzing to come together from the interdisciplinary fields is something we would love to do. So with that, I hope that as many of us as possible can go on this journey together to basically remember Semu, Sonia, the girl with cancer, the millions of others like them we can hopefully save. So that's it.